Recording in progress.
Hey kids, it's Matt here. I'm back with part two of net ionic equations. So now we're going to do single replacement, we're going to do double replacement, and we're going to do combustion. Okay? So the first of these, single replacement, these are all going to have a very similar look. So when we look at the balanced molecular, we have an element and a compound. And what we're looking for, that question that we talked about when we did our notes is, can calcium replace silver? When we look at the activity series, yes, that can occur. And we end up with these two products, calcium nitrate, because the calcium replaced the silver, and the silver is left out by itself. Now, silver is a precious metal, so it's going to be a solid. Now we're going to look at our solubility rules and go calcium nitrate is a nitrate and it is soluble, so it's aqueous. That's the balanced molecular equation. From that, we're going to take everything that's aqueous and we're going to split it into ions. And that's called a complete ionic equation. So, silver nitrate is aqueous. Split that into silver ions and nitrate ions. Calcium nitrate is aqueous. Split that into calcium ions and nitrate ions. The calcium and the silver at the far ends, those are solids. We only split aqueous. Only split aqueous. So now, if we look, we have nitrate ions and nitrate ions. And when you have something on both sides of the equation, those can cancel. Those are what are called our spectator ions, the ions that don't participate in the reaction. So now we remove the spectator ions, we write out the net ionic with the species that changed. We have calcium solid going to calcium ions. We have silver ions going to silver solid. This is my net ionic. And if the question asked, we would say NO3 minus ions, those aqueous ions, those are my spectators. Okay, the key here in blue, the state of matter cannot change between the molecular and the ionic. So if calcium was a solid here, when we get down to the ionic, calcium is a solid there. Silver, silver was aqueous. Silver was aqueous. It doesn't have a charge up here because it's in a compound. It has a charge down below because we've isolated the silver ion out. Same with calcium nitrate. It's aqueous, therefore calcium is aqueous, nitrate is aqueous. Silver is a solid, silver is a solid. The states of matter don't change. All we're doing is trying to represent the calcium dissolved and the silver precipitated. It came out of solution. Let's take a look at another single. Now we're taking a piece of zinc metal, throwing it in hydrochloric acid. And I believe we did this as one of our single replacement reactions in the lab. And so zinc is above hydrogen on the activity series. So the reaction occurs forming zinc chloride and leaving hydrogen by itself. Now keep in mind, the hydrogen is by itself. That makes it diatomic. The chlorine needs to be chlorine because zinc is in the triangle and has a charge of +2. So don't make chlorine diatomic over here just because. It's only diatomic when it's by itself. Okay? So then the complete, we're going to split, whoopsie, the complete ionic, we're going to split the aqueous. We're going to split the aqueous. And then we're going to find ions that are the same on both sides of the equation. And that's my spectator ion. Then write the remaining species with their states of matter, and that's my net ionic. That's showing me the zinc is changing, the hydrogen's changing, and they're changing their states of matter. That's what's going on here. Okay, those are single replacements. We got to check the activity series to make sure they're going to work. Now, let's look at double replacement. In a double replacement now, we have two compounds, aqueous, aqueous. And I said earlier in the first video, aqueous, 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 solid. Real common. This is my proof that a reaction occurred, a precipitate formed. And so I can automatically bring this iron down. Okay? I don't have the complete ionic written here because once we get comfortable with these, we don't need it. We need to look at what changed. We made iron carbonate. How could we do that? Well, we're going to take some carbonate ions here. We're going to take some iron ions here. And if those were both aqueous, so they're still aqueous. And when we combine them together, that's how we form the precipitate. So really, these are almost easier if we look at it and work backwards. Okay, find the solid and find out what ions you need to make that solid. Let's try it with another one. This one says write a balanced molecular and a balanced net ionic. So we have lead chlorate, aqueous, potassium hydroxide, aqueous. We're forming lead hydroxide. The solubility rules say hydroxides are not soluble. Not gonna dissolve. This potassium chlorate is soluble. It's aqueous because it has a potassium. Potassium makes things soluble. So let's start with our solid. Boom, bring it down. How do we form lead hydroxide? We take some lead ions, we take some hydroxide ions, and we form lead hydroxide. What are my spectators? The things that are aqueous at the end, potassium and chlorate. Potassium was aqueous on the left, chlorate was aqueous on the left, and they're both aqueous on the right. They did not change. They started out dissolved in solution. They finished dissolved in solution. Reminder again, spectator ions are always aqueous. So if it asks you to list the spectator ions, please list their states of matter. I say this in class a lot. States of matter matter now. Let's look at our last one, probably the easiest one to deal with, combustion. These don't change. You're being given a gas and a gas. It's going to make, and these always make, CO2 and H2O. What's different about these is these are both going to be gases. The water will be a gas here because we said in our notes the first time, these usually require energy. So we're igniting something. We're lighting something. We're burning something. That burning is a chemical change. So the The balancing is a little bit tough. I've got four hydrogens, so I put a two there. Two times two gives me four hydrogens. Got four hydrogens. That changed my oxygens. I have two of them there and two of them here. So I got to have four oxygens. Same thing happens when we do this propane. I balance the carbons with three. I balance the hydrogens with four. That gives me 10 oxygens on this side. So I've got to put a five there. But the molecular equation and the net ionic equation are the same. So if it says, what are the spectator ions? There are no spectator ions for combustion. The only time we're going to have spectator ions are going to be in single replacement and double replacement reactions. So those are states of matter and net ionic equations for all five states of matter. All right, this is a topic students have had trouble with, so I hope these videos help, and I'll look forward to seeing you guys in class.